Okay, moving on with the chapter 26 problems. This is problem number 14, which states the following. A young woman with normal distant vision has a 10% ability to accommodate. That means it increases the power of her eyes. What is the closest object she can see clearly? Now, on average, and according, you can look at some of the examples in the textbook. The power of an eye is 50. This person can adapt up to 10%. So the power can go up to 10% of 50, which makes the maximum power this person can have is 55 dioptries. And so the power is equal to 1 over f, which is equal to 1 over di plus 1 over do to the like this. And so do is p minus 1 over di, everything to the minus 1. That's the distance of the object. If you plug in the numbers, 55 as dioptries, the distance of the image, okay, is the distance in the eye, and even in this case, the eye is 0.02 meters. So the distance of the object is 20 centimeters. Okay. The other problem that I'm going to discuss here is number 27 here on the right board, and that involves the application of a microscope. So for this example, you want to keep in mind figure 26.16 over here, which I try to replicate here. Hopefully you'll be able to see everything in there, both in black and blue. So a microscope has two lenses, an objective lens and an eyepiece. Okay, so the object that we see is up here, is this right up top pointing arrow, and this is your objective lens. So the light that I dash here, two rays here, one horizontal ray that pass through the lens and then cross the focal point as FO. So that's the focal point of the objective lens. You barely can see that, and then continue out to the tip of the arrow over there, which I call HI. HI is the height of the image. The second ray that I pointed starts from the same tip of the arrow, but this time crosses the focal point in front of the lens. So continue straight, and once he hits the lens, continues horizontally. Okay, these two rays tell me that they cross over here, which means that the image produced by the objective lens is upside down, and that is the height of HI. So just look at the objective lens. We have the DO is the distance from the object to the objective lens, and DI is the distance from the lens to the image. Okay, so let's stop here for a second, because the first part of the problem asks you, what is the magnification produced by a 0.15 centimeter focal length microscope objective lens that is at 0.155 centimeter from the object being viewed? So we have the thin lens formula, 1 over DO, 1 over DI equal 1 over F. We've been given the distance of the object, which is 1.55 centimeter. And we have given the focal length. And so we want to find the distance of the image, this distance here. So if you plug in the numbers, you get 4.65 centimeters. Okay. The question is, what is the magnification? Well, the magnification of the objective lens, so MO, is minus DI over DO, which is minus 30. As we expected, the image is bigger than that and is like upside down. That's why the minus sign. Now the microscope also has another lens, which is the eyepiece over here. And so now this image here becomes the objective of the object of this other lens. I didn't draw the diagram here, the ray tracing here, to not complicate this diagram, but you should look at the image in figure 26.16 to make sure that you understand how the final image, which is this one over here, which is virtual image, actually is produced. Okay, so what is the question B that we have here? The question is, what is the overall magnification if an 8 times eyepiece, one that produces a magnification of 8 times, is actually used? Well, we know that the total magnification is just the product of the magnification of the objective lens times the magnification of the eyepiece, which I marked as an E. And so the total magnification is going to be minus 30 times 8 minus 240. And this is not a scale, but that's what it means. It means that your image is 240 times the original height and is upside down. Okay?